In these final slides, we're going to talk about how we can predict, knowing the pH of a particular solution, let's say a water body, we can predict what sort of species we are going to have, what sort of redox species we're going to have in that solution, in that water body. And that's what we call Pourbaix diagrams, so PHPE diagrams. And the name comes from the French chemist Pourbaix that came out with the idea. He was a 20th century French chemist. Before we go into actually what the Pourbaix diagrams are, we need to think about what the redox properties of water. Water is very stable against, well, it's very stable against many things, but about oxidation and reduction. But there are some compounds, very few, that are able to decompose water, to break it down. If water undergoes an oxidation reaction, then it liberates oxygen. So this is how the oxidation of water would look like. So a compound that is capable of, there is a strong enough oxidizing agent, will be able to break down water into oxygen and liberate oxygen gas. Under extreme reducing conditions with a very, very strong reducing agent, then water could decompose and liberate hydrogen. That is the reduction reaction for water. These reactions, and it's beyond the scope of these videos, are actually slightly dependent on the pH. And this is the equation. So it will depend on the reaction itself, the oxidation of water and the reduction of water, and also of the pH of the medium, more or less acidic. So we come up with, and these are actually, you can work out these equations. It's beyond the scope of these videos, and you use something called the Nernst equation. So you can come up with what we call the stability diagram of water. At what pHs and what electropotentials water will be stable, and what compounds will be able to oxidize water and liberate oxygen, and what compounds will be able to reduce water and liberate hydrogen. So this diagram, this stability of water, this fact that under extreme oxidizing conditions, water will split out and will oxidize and liberate oxygen, and under extreme reducing condition, water will reduce and liberate hydrogen, is what gives you the stability diagram of water. And only a species which changes slightly with pH, between very acidic to very basic, and only a species that have an electropotential within this boundary, this gray area here, a different pH, will be able to be stable in solution. Only the species that are within that boundary of stability of water will be able to exist in a stable form in solution, because they are above or below that safety zone, that stability zone, they will be able to decompose water. So that's what we use, that's what underpins our understanding of what species are going to be, what redox species for a particular element will be stable in water at different pHs. The fact that they need to fit within that stability zone. If their electron potentials fall above or below this zone, then they will be able to decompose water, either oxidize it or reduce it. So we can come up with something called PHPE diagrams, or also called Pourbaix diagrams, because of the French chemist that came up, did a lot of work on this area and came up with this idea. In a Pourbaix diagram, you do not represent, funnily enough, the electropotential. You represent minus log of the electron potential, and that's where the P stands for. As pH is minus log of the concentration of hydrogen ions, PE is minus log of the electropotential. And for a substance to be stable in water, so not to the oxidized water or reduced water, needs to have a PE value from around -12 to +25. So if the PE value is within that framework, that substance will be stable in solution. When you have a very negative value, so that means it's very low in the diagram, if you think of this as PE and pH. So a substance that has a very low, a very small, a very negative value of PE means that is stable under very reducing conditions. And for example, that would happen if you have an environmental system where you have very little water, like very stagnant waters, for example in swamp, so very anoxic conditions, very little oxygen, and very high, a very large, a very positive value of PE indicates very aerobic conditions. So it means you are in waters that are very well aerated. So there is a lot of oxygen. So they're very oxidizing conditions. And this is roughly where the different waters will fall in a pH-PE diagram. Again, the low negative numbers are very reducing conditions, so very little oxygen. High PE values, very positive numbers, very oxidizing conditions. And you have from, rainwater or lakes or river oceans that are very aerobic conditions to marine sediments, so well, below well into the water, or swamps, submerged soils that have very reducing, very anoxic conditions. So at any pH, we can use these, and these two lines are, as I mentioned before, the stability of water. Any species that produces ions that are stable in solution, redox species stable in solution, need to fall in this stability diagram. If they're above that line, then they will split water and will liberate oxygen. If they are below that line, they will reduce water, they will produce hydrogen. They will not be stable in water. And you can create pH, PE, pH diagrams for any species you can think of. Arsenic, chromium, copper, sulfur, and I've got a couple of nitrogen. I've got a couple of examples in later slides. And what tells you is by knowing the pH of the sample, or simply by knowing roughly, oh, this is a swamp, or this is a river, or this is an ocean, it gives you an indication of what species you're going to have. Yes, you're going to have arsenic, but exactly in what oxidation state? As an arseniate, you're going to have sulfur, but how will you have it? As a sulfitric acid? Will you have it as a sulfate? And all that you can infer just from knowing the pH of the sample and knowing exactly what species you're looking at. So it can be a good indication of what is the oxidation state of that particular species. Typically, not always, but typically maybe a metal ion or a pollutant or a chemical of environmental concern, arsenic, chromium, cadmium. In what state you're going to have it, what oxidation state we're going to have it. And that's important because different oxidation states, very oxidized species, very reduced species, they are more likely to react in a negative way for the environment. So how can I use these two pieces of information? Roughly the different conditions oxidizing or reducing of different types of water, the pH, and the Purbeck diagram for a particular element. So for example, I've got here the PE-pH diagram for sulfur species. And as you can see, at different pHs and whether in more reducing or more oxidizing conditions, you have different species of sulfur. So imagine that I think of, for example, how would be, what sort of a species of sulfur would I find in a lake? Well, lakes here, I've got this little image, are around a sort of neutral, slightly acidic to neutral pH, and they are oxygen-rich environments. They're oxidizing conditions. So what sort of a species, how am I going to have my sulfur? But likely I will have it probably in the form of sulfates, which is they cover most of this area. So if I'm thinking of what will be the species, what form will my sulfur be in a lake at roughly neutral pH? Well, it will be most likely in the form of sulfate, which is the species stable in oxidizing conditions, because there is a lot of oxygen. So you have a very highly oxidized form of sulfur. And on the other hand, what if I have, what about sulfur in a swamp, in a submerged soil, in a reducing environment? Well, swamps have in general, reducing environments. They are very short of oxygen. They are very stagnant waters, very anoxic conditions, lacking oxygen, and they have a pH roughly towards the acidic neutral, 4 to 6 pH. So I would say that I'm somewhere around here, and that my compound, my sulfur, will be mostly in the form of sulfhydric acid, H2S. So again, just knowing what type of water I've got, a swamp, a lake, an ocean, and some indication of the pH, I am able to predict what is going to be the sulfur species more abundant, more stable in that particular environment. And this is all for me. I hope it was useful. Redox is a moderately complicated topic if you haven't come across it before, but hopefully this series of videos have given you an indication of what redox actually is, the need for a reduction and oxidation to happen at the same time, and some of the issues surrounding redox reactions, both in a biological context and also an industrial context. If you're thinking about, for example, the spontaneity of reactions and whether you can have a galvanic cell or an electrolytic cell, and also in an environmental context, how you can use electropotentials to predict the form of a particular pollutant or chemical of interest in the environment just by looking at the pH of the water and the stability diagrams of that particular species. And this is all from me. Thank you for watching.